Okay, our next speaker is Yiming Chen. He'll tell us about Fortuity and Bootstrap in supersymmetric quantum mechanics.
Okay. Thanks for the organizers for putting together this nice workshop, and I'm very happy to be here, and thanks for inviting me to speak. So today I will continue this theme of Fortuity, and I will talk about a paper that came out last November and some work in progress, both mostly by myself. As we've heard from previous speakers, by now we've had many examples of Fortuity. So here I drew an axis. On one end, we have these higher dimensional field theories, the n equals 4 super Mills theory, ABJM, D1, D5, etc. And on the other hand, me and my collaborators have studied the n equals 2 supersymmetric SYK model as a toy model for Fortuity. Now, I want to put this on the same slide to highlight the difference between these different systems. So on one hand, we have this very specific Hamiltonian. And on the other hand, for this SYK model, we have disorder, and we need to do some average to solve the model. On the other hand, the benefit of SYK is that it's solvable at large n, and you can extract many universal features from it. While for these higher dimensional field theories, so far the analysis has been kind of limited at small n, mostly based on some numerics. So my motivation, wait, what's going on? Okay, so my motivation in thinking about this recently has been to try to find some models that kind of sit somewhere in the middle. And I want to have models that does not have disorder, but still retains some solvability. And hopefully by analyzing such models, the techniques that are used can in principle be generalized. They help us to understand this precise model a bit better. I want to advertise that Anna tomorrow would also talk about the model without disorder that still maintains some solvability. I don't see Anna here, but I recommend you to come to her talk tomorrow. So I would say that my model is strictly less interesting than her model. But one benefit I would say of what I'm going to talk about is that I will focus on a model that is a matrix type system. So the kind of techniques that we will talk about in this talk would be probably easier to generalize to, let's say, n equals 4 super Mills. Okay? So as Yiming already discussed, the definition of Fortuity requires this notion of inclusion of Hilbert space from smaller n to large n, and looking at how the supercharged Q interplays with this inclusion. Now, since in different theories, this notion of Hilbert space inclusion would, in general, be different. So it seems you need to work hard in different theories to figure out what's the notion of Fortuity. But let me just make some further comments about Fortuity, that there is this common trait that usually often appears that help us to identify fortuitous states in various theories easily. Most notably, as was observed in many toy models, we see that the fortuitous state kind of concentrate in the sense that they tend to only exist with quantum numbers that explicitly depend on n. So let me elaborate that a little bit more, as that would be one of the features that would be interested in this talk. It's not working. Okay. So let me just explain this concentration a little bit in more detail. So more precisely, after we fix all the charges that commute with the supercharge, in the simplest case where we have just one complex supercharge and the U1 R symmetry, we are left with an R charge, let me denote that by R, that does not commute with the supercharge but commutes with the Hamiltonian. So the commutation relation of the R charge R with the supercharge in my normalization is that it equals to the supercharge. Now, a feature that is seen in SYK models, but we also expect it to hold more generally because it follows from this super-Schwarzian theory, is that fortuitous states seems to concentrate in sectors with very specific value of R charge. Namely, if we fix n, fix the particular number of degrees of freedom in our theory, then the fortuitous states would carry a particular value of R charge that depends on n. So I like to represent it in terms of this two-dimensional plot of this R charge as a function of n. And the statement, at least that is seen in many toy models, is that only along some red line, that R is a non-trivial function of n, do the BPS states reside. So the BPS states only live along this red line. So this plot can be read in two different ways. One is in the vertical direction. So let's imagine we fix a particular theory, fix a value of n, and then the statement is that only at some particular R charge we would encounter a large number of BPS states. But this plot can also be read in a different direction, in the horizontal direction. So there the idea is that let's focus on a particular charge sector, fix a particular charge, and in the large n limit, when n is very large, this plot tells you that there are no BPS states. Okay, so this is a signature of fortuity that you don't have any fortuitous states with fixed charge in large n. So as n is decreased, when you hit this red line, you suddenly encounter an exponential number of BPS states. So as Yiming discussed, that there are many of these non-BPS states that enter the BPS subspace at a particular value of n. But this plot also shows another feature that says that as n is further decreased from the red line, these BPS states are kind of short-lived. They immediately also exit the physical Hilbert space. They disappear by, in some sense, becoming null. So in the n equals 4 super Mills discussion, it means that they will become trace relations themselves. So, yes?
I have maybe a dumb question. Is this independence meaningful? Because I could take the n equals 2 squared k and quantize the fermions in a charge conjugation invariant way, and for any n it will be 0.
Yeah, so here I always imagine that to really define the R charge, because basically you're saying you can always shift the R charge by some constant that might depend on n. So here I always want to fix R charge equals to 0 as my Fock vacuum, because in doing that way, I have a notion of, in some sense, simple operators. In your way of doing things, the R charge equals to 0 will always correspond to very, very heavy operators that have like half of the fermions occupied.
The thing that has to have independence is the difference between the R charge of the BPS states and some reference.
Yes. So the statement would be that the reference R charge between the BPS states and the simplest state, the Fock vacuum, would have R charge that depends on n. So that's the statement. Yeah, sorry.
Sorry, you say rather they become non-BPS again, they become null states?
Yeah, they become null states.
Is there any reason to say
They become null rather than non-BPS?
Yeah, so let's say in this n equals 4 super Mills case, the fortuitous states are those that when you add Q on them becomes a trace relation at some particular n. Now as n becomes smaller, they are still Q closed because trace relations remain a trace relation. So they won't be just lifted. So what will happen is actually they become trace relations themselves. Okay. Oops, what's going on? Okay, so that's just some reminder of some basic feature of fortuity that we would focus on later in this talk. So as I said, I would like to have some simple model that is kind of in between SYK and this kind of more complicated matrix system that motivated me to think about what's the simplest possible matrix quantum mechanics that would exhibit fortuity. So it turns out that you can have fortuity just with a single matrix. So that's what I will discuss in the next part of my talk. This is not working. Okay. So let me just describe what the model is to you. The idea is we consider a UN invariant, a fermionic matrix model. So let's introduce a fermionic matrix, psi, which is an n by n matrix, and each matrix element is a complex fermion operator. And we take the supercharge to have a very simple form. It's cubic in the fermion matrix. It just takes the form trace psi cube. Okay? And if you're familiar with this n equals 2 SYK model, you can basically view it as a very, very special SYK model. It's a very sparse and non-disordered version of the SYK model. Okay. Now, it turns out that this model is really simple. It's exactly solvable. By the way, I want to emphasize that here I want to treat UN as a global symmetry instead of gauge symmetry. I would actually be mostly interested in the non-singlet sectors. So the model is exactly solvable, and to do that, it's useful to introduce a different basis for the fermions. So since the fermion field psi transforms in the adjoint, you can decompose it into the bases labeled by these adjoint by these SUN generators. So there is a piece that is the trace mode that is proportional to the identity, and then there are these m squared minus 1 additional fermions psi A. And in these bases, the supercharge takes a very elegant form. It's basically the structure constant of SUN FABC contracted with the fermions psi A, psi B, psi C. Okay, and from these, you can also see that this is some very special example of n equals 2 SYK model. And the trace mode simply decouples. So in the later part of the talk, we would sometimes just ignore the trace mode. Okay, let me just use my computer. So using these bases, we can write down the following SUN generators. So these are the generators that are basically bilinear of the fermions. So JA is FABC times psi B, psi bar C, and they satisfy the standard SUN algebra. With them, you can construct the Casimir. So if you just go through a few more steps of algebra and compute the Hamiltonian of the model, which is the anti-commutator of Q and Q dagger or Q bar, you find that it's simply given by an identity piece, so some C number minus the some number times the quadratic Casimir. Okay, so it's extremely simple Hamiltonian. And in that sense, the model is exactly solvable because once you figure out how this fermion Hilbert space decompose into various representations of SUN, you solve the model exactly. Namely, the energy of the states are purely determined with the SUN representation they carry. Okay? Now, interestingly, one funny feature of this model is that the singlet state actually have the highest energy. So for them, the quadratic Casimir vanish, and then the energy actually is the highest, while the lowest energy states of this model, which in fact has zero energy, you can well, after we discuss a little bit more, you will see they actually have zero energy, are those states that are transforms in the representation with maximal quadratic Casimir. So if the C2 takes maximal value, then the two terms cancel, and those are the BPS states, or the zero energy states. So let me denote this representation by R star. And now I would discuss a little bit more what this representation is. Okay? So this representation R star has the largest Casimir one can possibly get. So now intuitively we would expect that it should contain a lot of fermions, because if you excite a lot of fermions, they would transform more non-trivially under SUN. And the optimal number of excitation is somewhere around n squared over 2, because basically that's half field, and there are a lot of states that can transform into each other. So that motivates us to find some states that has fermion number about n squared over 2 that would have the largest Casimir. So let me describe the construction to you. It turns out one can explicitly construct such a representation with using some basic knowledge of the SUN representation theory. So just to set up a little bit more notation, we remind ourselves that fermion matrix psi transform under SUN as an adjoint, and that is a little bit more manifest if we consider the following form of generators. So consider a generator JX that is a trace of a fermion bilinear and with additional C number matrix X inserted. And then if you compute the commutation relation of JX with the fermion operator, it simply is given by the C number matrix commutator of the matrix X and the fermion matrix psi. So in this way of organizing the generators, it's manifest that psi transforms like a adjoint, like a matrix. Okay. So let me just show you how this maximal representation can be constructed in the simple case of SU3. So the idea is that in the SU3, we can consider the following matrices, which we will use them to consider some generators. And these three matrices are the so-called, their generators are the so-called positive root generators in the SUN representation theory. So these three matrices are those that has some non-zero elements in the upper triangle. So E12 means it has a non-zero element in the 1, 2 position, and E13, E23, etc. Okay? So a highest weight state that we want to find should be annihilated by all these all these positive root generators. And that state is not hard to find. So consider the following state where all the fermions are occupied in the lower triangle. So consider a state where start with the Fock vacuum where no fermions are excited. We excite the fermions in the lower triangle of the 3×3 matrix. Then you can easily convince yourself that they are annihilated by all these positive root generators. For example, if you consider J corresponding to this E12 generator, a commutator with psi 3,2, what you find is that by commuting the matrix E12 and the fermion matrix psi, for example, it will move this fermion from the 3,2 position to the 3,1 position. Okay, so that's basically what will happen. And since in the starting state, the 3,1 fermion is already occupied, this JE12 generator will simply annihilate the state because all the fermions in the lower triangle are already occupied. And this statement holds for any fermion mode in the lower triangle and all the generators, all the positive generators, positive root generators that I discussed in the last slide. In other words, this state is then annihilated by all the positive root generators. One can then start from so this is the highest weight state. One can then start with this and act with the negative root generators to form the full representation. Okay? And this is not the only possible highest weight state. You are also free to dress this state that I discussed earlier by any additional fermions along the diagonal, which are in some sense the catan of SUN. And these are also new highest weight states, but with a different fermion number because you added some additional fermions there. So in short, what I just described to you, this construction applies for general SUN. So the idea is that one will build a highest weight state where all the fermions in the lower triangle of the matrix are occupied, so represented by this expression over here. And then we can dress it with arbitrary amount of fermions along the diagonal. So you can then multiply the state by any psi in the diagonal. And starting from the highest weight state, you can then build the entire representation. And we see indeed that such representations always have fermion numbers that are close to n squared over 2. So aligning with our original expectation that this would be some very heavy states with fermion number close to half of the total number of fermions. Okay? Now, you can also represent this representation R star with its corresponding Young diagram. And the Young diagram has an interesting shape. It looks like a staircase. So along the first line, there are 2n minus 2 boxes. And then the number of boxes decrease by 2 for each row. And in total, there are n minus 1 rows. With these, you can also compute what's the dimension of the representation, which is just the number of states in the representation. And you see the number of states is very, very big. It grows like 3 to the n times n minus 1 over 2. So it's some e to the n square number of states in each individual representation. So it's some very big representation. Okay, so after discussing this, let me now just convince you that indeed all these states are fortuitous states. Now, of course, you can go through this definition of fortuity. In fact, for this model, the notion of fortuity is exactly the same as SYK model. So you can try to understand it by looking at our SYK model. But here, I would not discuss the precise definition. We will just highlight that these states concentrate and they are very sensitive to the precise value of n. So let me discuss this. So we discussed the representation that holds the BPS states, and we see that their Young diagram depends on n in an explicit way. However, so to see that these states are sensitive to n, we imagine we can fix the shape of the Young diagram. So pick some particular Young diagram that is this staircase shape, while varying the number of n, try to interpolate different theories with different n. And we can see pictorially why such states are fortuitous. So imagine we fix a staircase Young diagram and consider n that is large, so 2n minus 2 that is greater than the number of boxes along the first line. So here what you will see is that the representation associated with this Young diagram will not be annihilated by Q. Basically, you can convince yourself that the fermions in the lower triangle are not fully occupied. So if you then act the supercharge on such state, it will not be zero. So the states corresponding to such representation are simply not Q-closed when n is big. When n is just the right amount that it matches with the number of boxes along the first row, Q acting on psi is equal to 0. Okay, so that that is what we discussed earlier. That the representation has the maximal Casimir, and in fact, if you compute the Casimir, you find that indeed they have 0 energy, so they are annihilated by the supercharge. Now, if you further decrease n just a little bit, so just when 2n minus 1 is even just slightly shorter than the number of boxes along the first row, then you see that this becomes an unallowed Young diagram for SUN because it now has number of rows that is greater than n minus 1. But for SUN, we can at most have n minus 1 rows. So this state will just no longer be a valid physical state in the Hilbert space. That's the sense that it just becomes trivial. Okay, is this clear? Okay, now we can package the information about the BPS states into just a function that we call the BPS partition function, and we introduce a fugacity Q that weighs the number of fermions in the BPS states. So the BPS partition function is a trace over the 0 energy sector with Q to the m psi. And then you see it takes the following form. So basically, Q to the n times n minus 1 over 2 corresponds to the number of fermions in the lower triangle. And then we should multiply it by this big factor, 3 to the n times n minus 1 over 2, which is the dimension of the representation. Okay, so the number of states in the representation. And then there is this Cartan part that I was mentioning earlier that basically you have n diagonal elements. So you can, for each of them, you can choose to either occupy or not occupied, so you have this additional factor. So this is the BPS partition function. And from these, you see that indeed you have an order n squared among the ground state entropy, and the number of BPS states is non-zero only in some finite window between n times n minus 1 over 2 to n times n plus 1 over 2. Okay, so it's like this kind of shape. Now, one feature I want to highlight in this model is that this model does have fortuity, but the BPS states are not quite concentrated as what you have in, let's say, the SYK model. Okay, so let me remind you that in the SYK model, in other words, if you choose the couplings to be random, what will happen is that essentially all the BPS states are in like order 1 number of sectors in the middle. Represented by this red line over here. In this model, it still has a pretty big width. It has a width that is roughly of order n. So that signifies like this model is less generic compared to a SYK model in some sense.
Sorry, this is more generic than SYK or less generic?
Less generic. Because for generic, if you choose generic couplings, they will concentrate. But this is some very special coupling so that they don't concentrate.
you expect in encode for Yang is like this or like SYK?
Okay, so here I'm not when I say generic, I'm only making a statement within this class of model that can be arrived by studyingCijk times psi j psi k. So this is some very non-generic choice ofCijk, basically this trace structure that does not concentrate. Now, I don't immediately know how to, the n equals 4 does not fit in this class, so my statement doesn't apply there. Now, for n equals 4 is an interesting question, whether to what extent they concentrate. Now, people have proposed, so maybe let me back up a little bit. So in the bulk, you see that the BPS black hole needs to satisfy some nonlinear charge constraint. So you could view that as some evidence that the states also concentrate. But people have discussed generalized black hole solutions that contain like gray galaxies or dressed by D-branes, so those will not concentrate, if those are indeed BPS solutions. So in some sense, if that is true, and also n equals 4 has also monotones, so you would say it's not really fully generic in this sense. They don't really fully concentrate. Okay? Other questions? Okay. Now, so in some sense, this toy model only captures some skeleton of the fortuity phenomenon, but did not manage to capture the interesting thing about it. For example, this R charge concentration as a consequence of Schwarzian.
So sorry, in this model, do you also have monotones?
No, there are no monotones in this model.
Okay.
And this model, obviously, as I have shown, is not chaotic. So all the states are not chaotic. Not just the BPS states. Even for the non-BPS states, they are not chaotic. So it does not capture this more interesting physics that we like to study. Perhaps this is as much as we can hope for, of course, from an exactly solvable model. Right? We probably won't be able to solve it if it's chaotic. So what is this model good for? So that's basically what I will try to explain in the rest of my talk. Is I view this very kind of simple model as a stepping stone to test some other techniques which can, in principle, be generalized to more interesting models. So I would highlight two things that I try to explore in this model, which I think should be you should be able to generalize to more complicated models, although the details I will mention is still work in progress. So one thing I will now try to discuss is to try to understand this model a bit using some collective field formalism, that is this unitary matrix integral that has appeared also in many previous talks. And the second thing I will mention maybe towards the end of the talk is to try to use this model as a benchmark to explore a little bit of large N matrix bootstrap technique in solving such BPS systems. So let me begin with these unitary matrix integral methods in trying to understand such models. As previously mentioned, an interesting feature that I really want to understand here is that this sudden disappearance of an exponential number of states. So if you are right on top of this red line, you have exponentially large number of states, but if you just move it a little bit, all of them disappear. And this, even though in this model the states don't quite concentrate in the same way as SYK, but the same phenomenon does happen, regardless that it does not quite concentrate and it's non-holographic. All the BPS states in the N theory, as you can check, they become null, or they are no longer physical states in the N-1 theory. So it's very sensitive to what precise value of N is. So microscopically, I explained to you that this is easily understandable from this oversize of the Young diagram. But I want to understand this from a different point of view. So for that, let me first try to rewrite the partition function, a BPS partition function, in a more suggestive way. So let's consider this expression in the large N limit. You see it can be written as something like e to the minus n squared times something that is a log 3q over 2. So whenever you see such an expression, you are kind of prompted to think that maybe you can understand this as some kind of saddle point, because it really comes with an order n square exponent. Okay, so you want to we would like to have some kind of large n saddle point understanding of this expression. So the kind of question I would like to think about is, can we find such saddle points, like find an integral to which this is a saddle point answer, and then we can maybe try to understand a little bit, like if it is a large n saddle point, how does it manage to disappear as n is decreased by 1? Because usually we think of large n saddle point as something quite robust, like it doesn't depend on sensitively on the value of n, but here apparently it's very sensitive to the value of n. So to do that, we use this idea of unitary matrix integral. So we will look at a closely related quantity, which is not the BPS partition function, but is the quantity that basically counts the multiplicity of the representation R star in the Hilbert space. So basically the partition function, but without this 3 to the n square over 2 factor. It is known that this can be written in terms of a unitary matrix integral, and such integrals are very familiar in the study of large n gauge theories. So the integral is the following. So it has 2 parts. So this exponential part, which has appeared in the last talk as well, is this plathesis exponential, basically constructing all the states that you can all the states in this fermion Hilbert space. So to do that, you just have this character for the adjoint, which is the matrix psi that we had, and all these also this single fermion partition function, which is just q to the n weighted by some -1 to the n plus 1. So that is this part. And then, as the previous speaker also emphasized, there is an integral over u that projects us to the singlet state. But here, importantly, I'm not interested in the singlet state. I want to project to this representation R star. So that's why I inserted this character chi of R star, which is a function of the unitary matrix U. And then by doing this unitary integral, you compute the number of multiplicity of R star in the Hilbert space. So in the following, I will kind of be very careless about this 1 plus q to the n factor, because for one thing, it does not really affect the large n analysis. And then the answer of the integral should just be this q to the n square over 2, which if you write it more in the large n way, it's like e to the minus n square over 2 times log 1 over q. Okay? So now let me explain a little bit what I understood about this integral. I should say my understanding of this integral is very poor. I only understood it in some special limits. So if you have any idea of how to improve it, please let me know. So the idea of usually how you would analyze this is to diagonalize the unitary matrix U, so denote its eigenvalue as e to the I theta, where I runs from 1 to n. And then you can explicitly compute what this character is. This character has a simple form that is a product over I less than j with each term is 1 plus 2 cosine theta I minus theta j. Now, what makes this problem tricky is that the character is not positive definite. Because you see, if you plot this 1 plus 2 cosine theta function, it is positive when the 2 thetas are close to each other. For example, when the 2 thetas are close to equal, you get 3. But when the 2 thetas are separated by some large amount, let's say pi, this actually becomes negative, right? It becomes minus 1. 1 minus 2 equals minus 1. So you get these. The first thing you would try to do, if you see this expression, is you would try to exponentiate this expression into the action, right? And then try to find some saddle point of the combined action of the original one and the exponentiated action, which in terms of the eigenvalue distribution rho of theta takes the following form. But what's subtle is here, since this is not positive definite, this action actually becomes complex. So it's a bit hard to analyze.
Yiming?
Yes.
At least one comment that sometimes appears in Chen-Simons when you want to insert Wilson loops to exponentiate the character by writing a quantum mechanics that has that representation as the Hilbert space.
I see. Okay.
Yes. In the action in a more conventional way. I don't know if it's helpful, but
Maybe. So, but to do that, in the end, maybe you will try to find some saddle point not just for U, but also with some other variables, maybe some combined problem.
Because in Wilson loops you have traces over representations, and then if you want to exponentiate it, that's not. You cannot just directly. But okay, that's the context where that is used.
Okay, thanks. Yeah, I haven't tried that. Maybe that helps. So one can try to analyze this problem with complex potential, but for this talk, let me try to adopt a different strategy, cheat a little bit, and do something else. So we would follow a different strategy that is maybe familiar in the study of indices, where we complexify the fugacity Q in a way that we basically cancel out the oscillating sign in the character. Okay? So the idea here is that if you expand out this plathesis exponential, the whole expression takes this form. You have this 1 minus cosine theta, which comes from the measure. That comes from this, basically the Van Neumann determinant from this integral over unitary group. And then there is this 1 plus 2 cosine theta that we had on the previous slide. And then if you expand out these, you get this expression that is 1 plus q squared plus 2q times cosine theta. And that you can also factorize it. To understand this factor, you can think of it as the product of two terms, 1 plus q e to the I theta I minus I theta j, and another that is the conjugate. So you can roughly think of that as coming from psi ij and psi ji, these two matrix elements. So now a fun observation is the following. If you complexify q in a very specific way, you choose q to be e to the plus minus I pi over 3, then you see that you can, after you factor out an overall phase, this factor 1 plus q squared plus 2q cosine theta is equal to 1 plus 2 cosine theta. Okay, so by doing that, what you end up with is a positive definite integrand. Okay, so basically this after you complexify, this piece cancel out precisely this oscillating sign of the piece in the character, and you just get a very simple integrand, which in fact, up to this overall phase, you can rewrite it as this very simple expression that is the absolute value of e to the I3 theta I minus e to the I3 theta j squared. And this expression is probably familiar to many of you. That is the usual measure factor of a unitary matrix integral, but now with every theta replaced by 3 theta. Instead of having theta in the expression, we now have 3 theta in the expression. So we now, well, after you arrive at this step, you know very well what the answer to this problem is. The saddle point configuration to this problem will be configuration where 3 theta i's are spaced uniformly on the circle. Okay, so that's what the saddle point configuration for the unitary matrix integral with only this measure factor is. However, what's interesting is that if you move back to the original theta variables, this gives not just one single saddle point, but in fact a large number of saddle points, because after fixing 3 theta, the theta is not single valued. Basically, you can, let's say you fix 3 theta to be 2 pi k over n. The theta can be 1 over 3 times that plus any multiple of 2 pi over 3. Okay, so that shifting thetas by any multiple of 2 pi over 3 will give you exactly the same saddle point in terms of 3 theta. So they are all like equally well saddle point contributions to the original integral over theta. Yes?
We think of saddle. I thought that when we think of saddle points of these matrix integrals, we shouldn't think of the thetas at specific locations, but in terms of the density of thetas.
So
roughly the same, so it's not completely clear.
right. So here, really, I mean the just in terms of the individual theta integrals, it's a saddle point of this integral. But indeed, I agree that in the large n limit, one would like to also think about in terms of this density variable rho of theta. So in that language, these are in fact not valid saddle points. Basically, the fact that you have this large number of saddle points translate into the rho of theta language as that problem actually has many, many zero modes. So if you decompose the rho of theta into Fourier modes, rho of n, all the modes, only the modes with n that is multiple of 3 are massive, while all the other modes are zero modes. So in that language, they are not truly saddle points, and you need to integrate over all these zero modes. But so here, when I say these saddle points, I just mean in terms of these discrete eigenvalues. Good. So indeed, that's kind of a peculiar feature of this model, that there are these zero modes in the continuum problem, which I view it as maybe one signature that this model is not holographic. There isn't like a particular bulk geometry corresponding to these BPS states. It's kind of it's not very holographic in that sense. Okay, but let me continue. So let's say you find some equilibrium configuration for these thetas. For these 3 thetas, let's say you have 4 of them, then you could, in principle, map it into various equilibrium configurations in the original theta variable on the sphere. Now, the number of such configurations, even though large, it does not scale as e to the n squared, because basically for each theta you have these 3 choices, so it only scales e to the n. So the number of saddle does not change the large n action. It's also well known that the original uniform saddle point has 0 large n action. So basically, once you focus on these configurations, the action is just 0 in the large n limit. So the entire large n piece of the action actually comes from this factor that you factored out, which is just n squared times n pi over 6. And you can check that for this specific value of q, it indeed reproduces the original answer. Okay, so we didn't really kind of we reproduced the correct answer, but the correct answer kind of comes from this trivial phase. It doesn't come from this perhaps more interesting part of the integral. As I was saying, the fact that we do not have a single large n configurations, but rather a variety of them, might be vaguely reflecting the fact that the model is non-holographic. Namely, we do not have a single classical bulk geometry, but rather it has these 0 modes I was mentioning earlier. Okay, so now one thing I want to do with these, even though it's kind of peculiar, but I still want to see that how do we understand the disappearance of all these saddle points if we just decrease n by 1. You see, they all contribute equally, but from the microscopic answer, we know that they should somehow disappear if we decrease n by 1. So to do that, we need to properly formulate this question. So we want to say, basically, the idea is that we want to hold fixed this representation and then change n. We don't want to also rescale this representation at the same time, because then you will just always get the same answer. We want to hold fixed the representation while decreasing the number of degrees of freedom. So that's what I explored in this model. And there is actually a very natural way to ask this question in our current context. So we simply ask how many copies of representation R star we can get if we try to decouple the last column and the last row of fermions. If I only allow you to include the n-1 block of the fermion matrix, then you should find that you are no longer able to build this representation R star. So in terms of the integral that we were doing, this means that basically I can try to write down an interpolating partition function where I still have the same measure factor, the same character piece, and I include all the fermion contributing in the 1 to n-1 block, that is this factor. But for any fermions that are in the last row and last column, I insert an additional lambda factor, which penalize the inclusion of such fermions. So at lambda equals to 1, we just have our original integral with the original configurations that we found. But now if we go to lambda equals to 0, we should instead find 0 for such an integral, which is not manifest if you just stare at this expression, how that happens. Because naively, you would say that just throwing away this piece does not change the integrand that much. So why do all these saddle points disappear? So that's what's curious about this integral. Okay, so let me just try to tell you what actually happens in this case. So let's still try to understand this for this special value of Q that we discussed earlier. It turns out that the saddle points are still there. So even if I throw away this piece, set lambda equals to 0, you can still find saddle point configurations for the 1 to n minus 1 eigenvalues. So they still have these equilibrium configurations. But one thing you might wonder is that then you will still have an integral over this theta n variable. So you find this configuration for theta 1 to theta n minus 1, but then maybe the integral over theta n somehow makes the answer 0. That actually is not what happens. So you can fix a saddle point configuration or this configuration for theta 1 to theta n minus 1 and study the integral over the remaining eigenvalue theta n. You find that actually the answer is non-zero. You actually can find some instanton configuration for the theta n variable, and it actually gives you a large contribution. Now, the way that the answer finally actually conspires to be 0 is that the saddle points no longer add up. They are instead dressed by prefactors depending on theta n. So individual saddle points don't contribute, but actually their sum, they now come with oscillating signs, and their sum becomes 0. So let me just explain that very briefly, how it works. So let's say if you just look at lambda equals to 0, and you write the integrand in this form, so you have a form that, you have a term that includes the first 1 to n minus 1 eigenvalues that still takes the same form, but then it's dressed by this additional factor that involves the theta n variable. Okay? And if you fix a particular configuration of theta 1 to theta n minus 1, this expression in terms, in fact, is non-zero. But the idea is that we don't just have a single configuration. We should sum over these saddle points where the theta i's are shifted by this 0, 2 pi over 3, and 4 pi over 3. And it's this sum together with this oscillating factor depending on theta n, that makes the answer vanishing. So that's what you can check explicitly, that if you sum over such shift, this additional factor, in fact, equals to 0 identically. So that's the mechanism through which this different configuration, in fact, cancel out, and you get 0 precisely when you go to n minus 1. But here I went a bit fast because of time. In the paper, you can see a little bit more discussion on this effect. Okay, so let me just summarize to make the point clearer. So let's summarize the model so far. So we saw that indeed you have exponentially large number of zero energy states in this largest representation. All such states are fortuitous, even though they are non-chaotic and do not concentrate sharply. Now, they can be identified with a family of large n saddle points, or in terms of this eigenvalue distribution, this continuous moduli of configurations in the unitary matrix integral. Now, usually these saddle points, they add up. However, if you try to change n to n minus 1, they are dressed with these oscillating phases, and they cancel out delicately and gives 0. Okay. So I'm not very satisfied with this story because of the fact that in the actual holographic systems, we don't expect such a large families, continuous family of saddle points in the large N limit, we are familiar with this idea that the BPS black holes are corresponding to some particular bulk geometry. So in that context, I don't really know what should happen, right? Because here it seems to depend on this cancellation of these many configurations. But in actual holographic examples, if you just have one saddle point, it's not clear like what's the mechanism that it would disappear when you go from n to n-1. Perhaps there is the integral of this theta n that makes the answer vanishing. But that's something I haven't been able to understand. If there are no questions, I'll move on to the second topic. Yes, Hong.
I'm confused. When you say saddle point, what are you expanding? You are not expanding in n, right? You keep the n finite when you go from n to n-1.
Yeah, I guess this is same as Juan's question. So maybe I'm abusing the terminology a little bit. I shouldn't really say saddle point. So in terms of the large N variable rho of theta, this will correspond to a continuous families of configurations. So as I said, there are these zero modes in the rho of theta variable. So it's a family of configuration that after you integrate over it, you get the correct large N action.
So in your calculation, did you do a discrete theta integral, or you actually did a continuous one?
In this calculation, I did discrete variables.
Right, for discrete variable, then what are you expanding when you call saddle point?
Perhaps, well, yeah, perhaps let me not use this terminology of saddle points. I should really say it's an equilibrium configuration of the original integral in the sense that if I take derivative of the original integrand with respect to the thetas, it equals to 0 on these configurations.
Yeah, just it's a stationary phase.
Stationary.
But there's no large parameter.
I agree, yes.
Okay.
I agree, yes. I shouldn't, yeah, perhaps the saddle point is a very bad terminology to use here. Okay, other questions? Okay, if not, let me move on to the next part of the discussion. So this part will be more exploratory. Is something that I've been trying to explore a little bit by myself. So now for the model I just described, you can solve it exactly, but let's say I just throw to you a more complicated supercharge. Like, what can you say about it? Like, how do you solve it? So let's say if I just write down Q equals to trace psi 1, psi 2, psi 3, is this model chaotic? Is this model in the low energy described by Schwarzian? And so on. It's not clear how you would approach such a problem. You might try to do some exact diagonalization of the problem, but for example, for this model, it's already very difficult already at n equals to 3, right? Because you have 27 complex fermions. It's not very easy to handle. So a general framework that can at least extract some information is the matrix Bootstrap. So I won't really review what this formalism is. I refer you to some other papers to study it. But I just want to highlight that such a technique seems to me is very natural also for BPS system, because essentially you are looking at the ground state, but the ground state in some fixed charge sector. So it seems like applying such technique to BPS systems allows us to direct access to heavy states as long as you fix the charge to be large. So just a few brief words on the matrix Bootstrap. The main dynamical input to the problem is this kind of loop equation. So take the commutator or anti-commutator of supercharge with any single trace operator. By doing that, you will get a superposition of single trace and a superposition of many multi-trace operators. So all these will be set to 0 if you evaluate them in the BPS states. And see, these are some dynamical loop equations, but of course there are also other kinematical constraints that people usually impose in Bootstrap, like the cyclicity of trace, etc. Okay, so you put all those in, and then you impose the positivity of a matrix whose entries are single trace operators. Okay? And by imposing positivity, you can then rule out some values of these operators and so on. So one thing I want to just highlight a little bit here is that usually people might denote this bracket as the expectation value in the ground state. That's not what we are doing here. So here the expectation value is some trace over the Hilbert space of some single trace operator O with an exertion of some projection operator or density matrix to some BPS subspace. Okay, so evaluating expectation value of some operators in the BPS subspace. And importantly, for most cases, this PBPS is non-unique, right? You can consider PBPS for various charge sectors and also superpositions of them. So it's not a unique choice of such P. But you can try to input what PBPS you are interested in by specifying some expectation value of single trace operator. Let's say single trace operators that correspond to some conserved charges. You can specify their value, and then you will be focusing on some particular BPS states in some charge sector. Good. Now, a question that immediately arises is what would you want to look at in such a bootstrap? Like, imagine you can do this, what would you want to compute, right? So one thought, there are various thoughts, but one very concrete idea is to try to use the bootstrap to constrain the distribution of BPS states. Like showing that, for example, showing the states concentrate. They only exist in some particular charge sectors, like in this single fermion model that we discussed. Okay, so this is, in principle, some interesting information we would also like to have in the n equals 4 supermules theory. Now, it seems to work. So I've been doing this with my collaborator, Claude Code. And of course, you need to be careful to verify the codes written by Claude. But basically, you can arrive at some sensible results. It agrees with the exact answer that we can compute in this single fermion matrix model. So what I'm plotting here is the horizontal axis is the properly normalized expectation value of trace psi bar. So that's the fermion number operator. Okay, on the vertical axis is some other 4 fermion operator, psi bar, or properly normalized so that they are like expectation value is order 1. So this plot is this bootstrap plot where the red region is ruled out. The blue region is in principle allowed up to some truncation order in the bootstrap. So the exact answer that we can compute analytically is 0.5, 0.5. Okay, but you see, well, I didn't try to go to very high order, but you can get some islands. And if I didn't know how to solve this model to begin with, then by looking at this plot, I would say, okay, all the states must be concentrated in some fermion number that is in the middle of like scale as n squared. So they must be fortuitous, and there are no monotone states in this model. So in principle, this could give you some information like that. Now let me discuss some more complicated cases. So for more interesting models with more conserved charges, the BPS states will be concentrated along some codimensional 1 slice in this space of charges. So I believe Matt tomorrow will also talk about models of this kind that contains 2 flavors of fermions. So this is a model coming from his paper with Joaquin and Wen Li. And it has some random coupling times psi j chi bar. So if you look at where the BPS states of this model reside, and plot it in terms of the fermion number of psi and fermion number of chi, please ignore this dashed line. The BPS states only reside along the red curvy line. Okay, so the BPS states concentrate along some codimensional 1 slide. And these can be roughly viewed as like the nonlinear charge constraint in this kind of toy models. Now, so then if you want to try to bootstrap this kind of model, of course, generalize it to matrix case, there's an immediate problem that you have to face. So the idea is that here, this concentrated line is in fact non-convex. Okay? It's non-convex because if you draw, like, for a convex set, if you draw a line between 2 points, the line should also still be within this subset. But this is non-convex. But in the simplest kind of linear programming, all the plots that you can get are convex plots. Of course, there are ways to, as I was informed by Bootstrap experts, that there are ways to work around that. But let's say you are just working within linear programming, then at best, what you can expect to get is a minimal non-convex set that includes this line. Okay. So you're not gonna really try to get to this line just by working within linear programming. So now let me show you what actually happens if you replace these couplings by some trace expression. So let me introduce two matrices, psi and chi, and consider the supercharge to be psi square times chi bar. In the Bootstrap, you see that the BPS states must reside in a band like this. And as you increase the truncation level, you see like this point does move to the left a little bit. So it's conceivable that in the large, if you improve the precision, maybe it will approach this kind of this kind of region. But okay, now the question is, how do you tell what really happens, right? If I just give you this as the answer from the Bootstrap, it's not clear whether the BPS states in the end really concentrate along the codimensional one slide or it still smeared over some region. So that's one difficulty you have to deal with to push this a bit further. Let me, I'm almost finished, so let me mention another difficulty you need to deal with is that, say you apply this to the 1/16 BPS sector of n equals 4 sigma Mills theory, or that is probably a little bit more too complicated, but at one loop there is this nice no derivative sector that previous speakers discussed that contains 7 matrices, which is perhaps pretty tractable in terms of what people have already done in terms of matrix bootstrap. Now, a basic issue here is that there are also monotone states which do not concentrate. So the monotone states are kind of everywhere. They can take various different charges. So since you have them, it would seem like in the Bootstrap you should just get no constraint at all because it's not clear how you would root out such monotone states from the Bootstrap. So one question I guess we could discuss, or maybe an interesting question I want to know the answer is, could there be a way to get rid of the monotone states in the Bootstrap, maybe by imposing some additional conditions, etc.? Okay, so as promised, the organizer says we should end with some discussion questions. So here I listed 2 questions that I would like to know the answer. One question that kind of concerned me a little bit these days is the existence of non-chaotic fortuitous states. Now, my model is very stupid. It's non-chaotic for even the non-BPS states. So perhaps it's not a surprise that the fortuitous states are non-chaotic. But it raises the question that could there also exist non-chaotic fortuitous states even in actual holographic systems, let's say in the large N limit. Now, if such states exist, they will probably correspond to some geometries without horizons. What would be their bulk interpretation? It will have to be some horizonless geometries that are formed not by like collecting these multi-gravitons and form a bound state, but by maybe, is there a question? Okay, by collecting like non-BPS stuff to form like very delicately some bound state without horizon. It seems unlikely, but I'm not sure whether one can really rule it out. Now, another question is what I was talking about earlier is in the Bootstrap, what kind of questions we can ask and whether there is a way to get rid of the monotones or at least separate them from the fortuitous states in some way. So with these questions, I'd like to thank you for your attention.
Questions?
Hi. Yeah, maybe just as a comment to your last point is that so this SU3R singlets, they don't do a perfect job, but they project that condition projects out a lot of the monotones.
Okay.
Whereas it keeps it also projects out some fortuitous operators, of course, but it keeps. If you would compare the two, it seems you keep.
I see. Interesting. Yeah. Okay, I'll try to understand more detail.
Yeah, maybe I misunderstood your the sort of collecting non-BPS stuff to make something that's delicately exists as a BPS data file. And wasn't there an interpretation maybe by like Kasha and Pedro that you could identify one of these fortuitous states as like a bound state of some gravitons, but then a massive string state? It's small n, so it's a cartoon, but that seems to be a case where it's some massive string state in ADS5, which is non-BPS, but there's some gravitational well, and for a very special value of n, and
But those states, if you take the large n limit, are described by black holes.
Yeah, I agree, but
here what I mean is, could there be states that are fortuitous, meaning that they are not formed by product of multi-gravitons, but nonetheless non-chaotic, so we don't expect them to be black holes.
Right.
Whether there could exist such states.
But that small n looks like an example where it's using some massive string states, which are not multi-graviton type, and they're not a black hole type.
No, well, that's for like very small n. I don't know how you would say whether it's chaotic or not chaotic, or black holes or not black holes. Here I'm more phrasing this as a question in the large n limit.
Understood.
Whether there exists like families of such states that maybe has a lot of entropy, but nonetheless non-chaotic while still being fortuitous.
Right. Maybe a highly excited winding string or something.
Yeah, some kind of maybe.
Say that you want to do the 1/16 BPS and you go for super-Yang-Mills theory and apply this matrix bootstrap technique. Is it really hard, or is it okay to increase n? How large n do you think is reasonable?
No, n is taken to be infinite here.
Oh, okay.
It is like directly in the large n limit. That's why maybe it's interesting. It complements this finite n story that people, including you, have been studying. Here, n is already taken to be infinite, so there, at least in this truncated sector, there are 7 matrices. I actually already did it, but I don't know what to look at, and I didn't get very nice islands, so I didn't show any of the plots.
But then in the n equal infinity model, the monotone states are totally counted, and it was accounted for in 2005 by Kenny Maldas and Binola.
Yes.
Can you use that? Because you have a definite monotone spectrum, you can have that spectrum as a right-hand side of the bootstrap equation, and try to constrain the unknown part of the problem on the left-hand side.
That would sound like you would focusing on them instead of ruling them out. I don't know how you would.
Okay.
Yeah, how you get rid of them, in some sense.
We can discuss later.
Of course, one can try to do some finite n bootstrap. That's in principle one thing one can try to do. But here I only did large n. Question, Joaquin?
If you would do finite n, I don't know much about the matrix bootstrap, but is it useful to ask questions like what is the gap to the first excited state?
Exactly. So that is another important target of this bootstrap program. In the large n bootstrap, you wouldn't be able to get the gap. At least that's what I discussed with Espers. What they told me. But if you do finite n including 1/n corrections, perhaps you can get some information of the gap. I haven't thought too carefully about it.
So this is the type of thing that the bootstrap can do efficiently?
I don't know whether efficiently.
Okay.
I'm not an expert on bootstrap. I'm just very.
Well, if there's no more questions, let's thank the speaker again.
Thank you.